So in this video I'm gonna be explaining the binary count. We are using Quartus Prime Lit edition. We are programming a code for a FPGA university program. This is a Max 10 from Intel. So as you can see, we are using the same three libraries as always: the STD Logic 1164, the STD Logic ARITH, and as the STD Logic Unsigned. So first of all, we are gonna be declaring the entity. So these are the ports we using in this practice. So the first one is the clock 50 megahertz. Is input of STD logic. The second one is a reset and is an input from the STD logic. The third one is a clock out, that is the output of the STD logic. And finally the counter, that is an output of the STD logic vector 7 down to 0. So it will be from 0 to 7. Now the architecture. The architecture behavioral describes the behavior of the bin count entity. So we have the signals, the clock temp. This is a 26-bit wide STD logic vector used as a temporary storage for the divided clock. And finally, we have the clock new. This alias represents the most significant bit of the clock temp. And also, we have the count temp. This is an 8-bit wide STD logic vector used to count binary occurrences. Also, we have the process clock divider, which has the sensitivity list. This process has sensitivity to changing the clock 50 MHz and reset. The behavior of this is the reset is high or 1. The clock temp signal is reset to all zeros, as you can see. If there's a rising edge 1 on the clock 50 MHz, the input clock temp signal increments by 1. In this increments by 1. And also the clock out will be now the clock new, assigns the value of the most significant bit of the clock temp to the clock out. In this part of this over here, the line 31. Now the process binary count. This has also a sensitivity list. This process has sensitivity to change in the clock new. Now the behavior. So if there is a rising edge of 1 on the clock new signal, the count temp signal is incremented by 1, as you can see here. Also, if the counter will be the count temp, the outputs of the bin count value stores in the count temp. So in essential, this generates a slower clock signal at the output clock out and counts the occurrence of the binary patterns with each rising edge of the clock signal. The clock divider resets it when the reset signal reset is assert 1. Now I'm going to be explaining the BHT. This is only for simulation processes. So this is auto-generated by Quartus, but this is the block of code that we made to have this working in the simulation. So it's a loop, as you can see. So basically, where it says begin marks the beginning of the process block. The clock loop. This is a loop label named clock loop. Keyword indicates the start of an infinite loop. Now the clock 50 MHz is set to 0, assign a logic low 0 to the signal clock. Then it will wait for 10 nanoseconds, pauses the execution for 10 nanoseconds. Then the clock 50 MHz is assigned to 1, so the signal of the 50 MHz is high, or 1. Then it will wait for 10 nanoseconds, pause the execution for another 10 nanoseconds, and finally it will end the loop. called loop. Indicates the end of the loop label, clock loop, since there is no exit condition. This loop will repeat infinitely. And that's all. Now we are gonna jump for the physical part. Hope you learned something from the code. See you in the next one. Hello, and so we are on the physical part. This is a FPGA University program. This is a Max 10. We're gonna be testing this program of the binary count. As you can see, if I put the switch down, the LEDs will be moving around. When I pull the first switch up, it will stop, as you can see. So I hope you learned something from this video, and see you in the next one.